MSF hiring.
Who?
89,000.
Who is?
Yeah, it was on the government website.
MSF? What kind of position? That's interesting. That's a high salary for MSHA. What were the qualifications?
I don't know.
That's interesting.
Downtown Manhattan.
No, it was like out in the middle of nowhere.
Interesting. No, there are jobs out there. But everyone. It's a matter of balancing things, and that's one thing I wanted to say last week, and we ran out of time, so we'll make time this week right now. But it's important to stop and take a moment to decide what's important to you. For me, what's important to me has changed, and it's always kind of changing, but it's changed over time. And when I can't remember if I told you guys this about myself, but I thought I wanted to be a medical doctor and did a year of medical school and realized the things that I thought were important to me really weren't that important to me. And so I changed my mind. When my plan B was to do public health, and sorry, it's hard for me to talk and do stuff. I like the sciences, and so I decided to, at U of A, which is where I was at, there were two concentrations within, they have several concentrations, and I chose to stick with environmental and occupational health. It was one of the more practical parts of public health. There's a lot of sort of fluff, I call them fluff degrees you could get in public health, but in terms of jobs, it just, there wasn't any science in them. I wanted something with science, and I chose environmental and occupational health. Within environmental and occupational health, there are sort of two branches. It's kind of like how this program is sort of split. One was focused mostly on environmental, meaning, which is what this class is sort of like that program in one class, but exposures caused by industry that first move to a community or the environment and then to humans. And the other is industrial hygiene, the occupational side, where the people actually working in the industry who are getting exposed directly by the health hazards. I was really focused on environmental health, and I was just talking to one of your classmates this morning. There was funding available for industrial hygiene, so not environmental health, but industrial hygiene, and I was dead set on doing environmental. So I felt like, so here's a disclaimer. I don't want to convince anyone of anything. You do what you want to do, but I felt like my professors were trying to convince me to do industrial hygiene because they kept saying, hey, there's this funding available if you want to focus on industrial hygiene. Like you could have, your tuition paid for. And it didn't take me too long, though, to realize, wow, well, maybe that money would be nice. And as I was looking at the job market in environmental health, there just weren't a lot of opportunities. So for environmental health, you can work at a state public health department. You could work for the federal government in some sort of capacity. You could go on and do a PhD and do research at a university. Those are pretty much the options. And I didn't like any of those, including getting a PhD. And anyway, it's kind of funny. Life is sometimes ironic, but there was an internship opportunity at a mine in industrial hygiene. I decided to take it, and I got it, and I didn't mind it. You know, I realized I wasn't super picky on what I did exactly every day. I just wanted it to be something that was fulfilling and that I at least somewhat enjoy. Every job is going to have its mundane parts where you question, you know, why am I doing this? And then other times where it's awesome and you love it. And I'm sorry, for some reason my slides aren't opening, so I'm gonna have to switch here. My point is, though, I think it's important to stop sometimes and think about what is important to you and base your decisions on that. So if there's something you are really passionate about, everything you do should try and take you there. Make sure that all your decisions are building towards that and will take you to that place. Yeah, I'm sorry. I'm going to have to reopen it on this computer. For those who are interested in ASSE, there is a, tell me if I've told you this, but there is a 1.5 day conference being sponsored by ASSP in Vegas, and it's mostly paid for. You'd have to pay $25 for registration. I am going to book a van, so your travel, you know, getting there should be covered unless you want to drive separately. Your lodging should be paid for. They provide breakfast and lunch, I believe. So lunch at least. And, you know, at conferences when they say breakfast, maybe you kind of know what they mean. It's like muffins, or, you know, these muffins that are mostly sugar and like white flour and should probably have a skull and crossbones on them or something. But anyway, so yeah, plus like fruit. No. I will put an announcement on Canvas. So or I'll send it through the ASSP. I'll piggyback off of one of Leanne's emails and send it out that way. So was it? I didn't make the meeting. Did she talk about it in the ASSP meeting? Oh, okay. All right. Good. So I'll send out an email with a link to the registration. The conference itself goes, you know, it should end like at 4 each day. So, wow. My computer is just being really, really, really slow. Let's see if it's fast enough to do this. It just came up. Anyway, there should be time in the evening for you to do whatever you'd like in Vegas. But, you know, so the way it's set up is we'll go the night before, stay the night at the lodging they provide, and a full day the next day.
So we go on Friday?
I think it's Thursday night. stay Friday, all Friday, and then Saturday, half day. So you have Friday night plus half day Saturday. If you ride with us, we'll be coming back, when it's done. If you want to hang out longer, then you can drive yourself.
How many hours is it?
Yeah, it's around 4 hours to get there. All right, I apologize for the delay getting ramped up here. I don't know what's wrong with my computer. We're going to cover some objectives, talk about controls briefly. We're going to review TWA calculations. So we did a little bit of that last time. We're going to talk about concentration and some calculations. And to be honest, a lot of what we do, you could think of it as an equation, the calculation with an equation, or you could think about it as unit conversions. So unit conversions. Talk about calibration and a couple of different types, primary, secondary, and then the lab. So I want to get to this point by 1:30. We'll take a 5 or 10 minute break and kind of mosey on over to the industrial hygiene lab. And I have some equipment set up. We'll talk more about the lab once we get there. And in the past, I've tried to organize the lab so that everyone had something to do at all times. It's just kind of hard. And I felt like the extra stuff was just busy work. I was just making stuff up so that everyone was here the same amount of time. So groups that come first, that do the actual lab exercise first, you can go when you're done. I don't see the point in, if there were 5 of me, then like I could do more, but there's only 1 and like 15 of you. So what we're going to be doing though is learning how to calibrate an air sampling pump. And that will be part of the lab. We'll be collecting data and that you'll all share with each other. And that lab report will be due, I think it's in a week and a half from today. So we'll talk more about that when we get there. But the objective of the lab is 1, to learn how to calibrate, and 2, to see the effect of different conditions on the pump. So there's a procedure for calibrating it. What happens if you change that because you messed up or whatever, you forgot? How is that going to affect your results? That's the objective of that. Kind of talked about all of this. We will talk about hierarchy of controls. We're going to talk about concentration in terms of parts per million and milligrams per cubic meter. There are lots of ways to measure concentration, but we're going to focus on just those. Is anyone familiar with this chart? You could apply it to not just occupational safety and health or industrial hygiene, but lots of different things. Of these options, elimination, substitution, engineering, administrative, and PPE, which do you think are more suited to, say, the design phase of a system or a process, whatever, any industrial setting?
Substitution.
Say those again, sorry.
Substitution. Yeah.
Okay, good. So it's if you are involved in the design phase of a process, it's relatively easy and inexpensive to change stuff while it's all just drawings on a paper or in a computer program. You could change the process so you would completely eliminate some hazards, or you substitute them for something less hazardous. Engineering, maybe some of that. Once it's built, so once the airport has been constructed, or the aircraft, or the chemical processing facility, it's kind of hard to do these. It's really expensive and really time consuming. And so you want to think about those, but they sort of go on the back shelf when you start to think about controls, because they're really hard. It just, you know that it's not going to happen unless there's some new technology or equipment that comes out. Then maybe this is possible, or maybe you don't know about it yet and you just need to figure that out. But generally, these you can do fairly easily in design. Once everything has been laid out and there's no going back almost, then you have to think about these. Now this is, this is designed to show that these are the most effective. You want to spend the most time thinking about these. And these comes down to the least effective. Why would PPE be the least effective, do you think? Okay, so you're relying on human behavior. It's never good to rely on human behavior, depending on the nature of your mission. If it's super critical, you might want to have some more redundancies in your system, huh?
It doesn't necessarily prevent injury as much as it mitigates it. I don't know if that's the right way.
Good. So going industrial hygiene, I think of like a respirator. If you are being exposed to, so maybe you guys can tell me, is there still lead in jet fuel?
Yes.
Don't. I mean, I thought so. I just wasn't totally sure. But so let's say you work on the grounds crew, and for whatever reason, the company's done sampling and they've determined that you've got a high exposure to lead from the fuel or something, and so you need to wear a respirator. It hasn't removed the lead from anything. It's still around you. You're relying solely on your own behavior in compliance to wear the respirator, but there are other things as well. How well does the respirator fit? If it doesn't fit very well, you can have a leak and you might as well not be wearing it. There are lots of things, lots of uncertainties. And if you want a system to be more reliable, you try to eliminate this stuff. Administrative still relies somewhat on people. Now we may have administrative systems that help sort of automate things, but there's still people involved, and you want to, and so if you can engineer it out, then that's the best. So I guess with the jet fuel example, if there is a jet fuel that doesn't have lead, that's something you could substitute. Or if you design an aircraft that uses a whole new type of fuel that, I don't know, it's more environmentally friendly and also for human health, that's an example of that you can use there. So point is, maximize what you can do at the top of that inverted pyramid and try to save the personal for last. There are going to be different teams you work in today. The stuff we do in lecture is just for today, but by the time we're over there in the lab, I would like you to have chosen one or two people that you'd like to work with for the rest of the semester. Now this is, again, you won't be submitting team assignments, but it will be helpful because it will facilitate some of our field exercises that we do. It's just easier for me to talk to like 3 or 4 or 5 groups instead of trying to get to everybody. Also, you may, like today, each group may be collecting certain data and then sharing with everyone else. Another example will be the ventilation lab we do. Each group will be doing something a little bit different and then sharing the data together for your lab report. So think about that. It's, you don't have to study with your group, though I recommend, especially if you kind of need to brush up on, algebra and some math stuff, finding somebody to study with. I can't remember if I mentioned it, but I would not have gotten through my undergrad science classes if I didn't have a study group. Finding other smart people, or maybe not other people smarter than me, finding people smarter than you say, hey, do you want to study together? Anyway, find somebody that you can study with that, you know, you can bounce ideas off of. But for right now, the team that I'm talking about, doesn't matter. Just find somebody to talk with about the differences between a hazard or a risk. It's kind of hard with that low resolution clip art there, but which one of these is a hazard versus a risk? So it's sharks versus a guy in the water with sharks. Which one is a hazard? Which one is a risk? Take like 1 minute. I guess we don't have pictures, so. We are going to get to some math later, and you might want to be more interactive than some of you. But yeah, I hear some good thoughts, and you're right. So the hazard is the actual danger.
Say again?
The hazard is the actual danger, and the risk, there are different ways it's defined, but it's often thought of as the probability or the likelihood of that danger, that thing occurring, coming into contact with someone, and the severity of the outcome if that were to happen. So the likelihood and severity of a hazard reaching a person, in this case. So like with sharks, unless Sharknado is a thing, if you've ever seen, I haven't seen that movie, but I guess. Well, I don't know if this is accurate, but I heard that the producers were serious when they made the first one. And the reaction from everyone was just that it was so ridiculous that it was funny. So the second one, they purposely, I think they basically followed the same pattern, but it was on purpose. Oh.
To make money to create cult classics, so when they produced that movie, they said, you have a $20,000 budget. Make something that is going to be so astronomical ridiculous. And you'll then create a series that will attract another talent.
Okay.
That's how they said that.
So what was the budget for the second one?
They're
Curious.
about $20,000.
Oh, really?
Yeah.
Wow.
All the cameos that you see people showing up, that's just somebody walking on set that day saying, hey, I'm in town, right? In the description. So,
Wow.
so I've never seen them, but
So unless sharks flying through tornadoes is possible, we in the upper highlands of Arizona don't really have a risk of, you know,
it does rain fish up in the boat.
maybe, maybe a little shark, I don't know, like right on your head. But, but I mean, it's effectively zero, right? The probability of us right now being attacked by sharks. And even if we were swimming in the ocean, the risk is still really small. It's just, you know, movies like Jaws. And with aviation, some people are just terrified of flying, and we're not very good at perceiving risk, to be honest, as humans. So you guys were right. And you want to prevent that hazard from reaching the person. So you can imagine if you eliminate the hazard completely, there's no risk, right? If you're using unleaded gasoline, there's zero risk that you're going to inhale lead as you're driving down the road. These are just some goofy examples. So just kill all the sharks, I guess. I don't know, that's not an option, but I guess you could have shark-free zones with nets or something. Although that's I guess an engineering control really there. But anyway, substitution, engineering, administrative, signage is important, but it's not very effective. And then PPE. Okay, so some review for time-weighted average. We talked about one, so we're going to get into some of the math. Let's do this. It's like one of the few times it goes up for me the first time. I'm amazed. Okay. So I think we used these same numbers last time. We did it for an 8-hour time-weighted average, which is what regulations are based off of. An 8-hour time-weighted average. We're not always interested in the 8-hour time-weighted average, though. So let's do this with a couple different scenarios. So we have this is from the glass blowing example. Instead of workers, we're going to say that this is different parts of the day. Same worker, but different parts of the day. We took 3 different samples during 3 different types of tasks to see what is exposure associated with each of those tasks or processes. So let's say we have task 1, task 2, and task 3. Last time, I made the math come out to be 8 hours exactly. It's rarely 8 hours exactly. If you take a sample, I mean, maybe you get to your sample early, whatever equipment you're using, and right as it hits 8 hours, then you turn it off. That's not usually how it goes, though. You usually take what you can get. But let's say we have it's 0.01 milligrams per cubic meter, 0.82, and 0.04 milligrams per cubic meter. And let's say, so think of the glass blowing plant. Let's say this person works with mixing for 2 hours. They clean up the broken glass for 4 hours. They I can't remember. Let's say they work in shipping. Now, it's rare, unless it's a really small facility, you wouldn't see this, but let's say they work in shipping for another hour. And the rest of the time is really like line out, which is, it's a term I'm familiar with, but when a crew meets together at the beginning of the day and everyone receives their assignment for the day, you can do this or this. I call that line out, just because it's what they called it at the mine. But anyway, line out, lunch, and like putting stuff away at the end of the day. So that last hour, you can kind of imagine there's not much exposure to silica. But we don't have 8 hours, right? How many do we have? We have 7 hours. So if we want to do a straight time-weighted average, not thinking about what we're going to compare to the Pell, to the standard, then it would look like this. We'd have 0.01 times 4 plus 0.82 times 2 plus 0.04 times 1 all over 7. This is the time-weighted average of our sample, but it's not an 8-hour time-weighted average. So what do you think we need to do to make it an 8-hour? The official equation that you'll see is C1 times T1 plus C2 times T2 plus Cn times Tn all over T1 plus T2 plus Tn. That's the official equation. So it's the same equation, but we need it to be 8 hours to compare it if we want to compare apples to apples. If we want to compare to the standard, it has to be an 8-hour time-weighted average. So I talked about lunch and prep, and so what am I not putting on here? There's something missing, lacking.
Well, you have to have it by 8 hours. Multiply it by 8 over 7. Multiply the entire time weighted average by 8 over 7. Because you're just scaling.
It's a good thought, but no. So keep thinking. Andrew? Good. So we would have another one, and the concentration is 0, and the time is 1 hour. I mean, we're assuming that when they eat lunch in the lunchroom, they're not breathing in silica. I mean, maybe they are, but we're making an assumption there. So because it's times 0, it's gone. But we do have the hour, so we have to add in that extra hour to get to 8 hours. Good. So let's do this one. In case you can't see, I'm going to be writing. So this is 200, 100, and 300. I usually use minutes because, again, rarely do things land right on the hour. How many minutes are in 8 hours? What's
480.
yeah, 480. Mm-hmm. Oh, that's not 300. Sorry, it's 30. We will talk about what you have to do if your shift is longer than 8 hours. But so I'd like an 8-hour time weighted average for this. These are acetone samples. Has anyone ever worked with acetone in their job? What do you use it for? Okay. It's a solvent, so it's good at stuff like that. And it's not extremely toxic, but still, you know, you don't want to be sucking it in all day. One thing I want to highlight, I think I may have mentioned last time, I just want to be sure that,
The units?
units will be milligrams per cubic meter. For now, we're going to convert those.
You saying translate these to hours?
Calculate a time-weighted average. So pretend we're sampling the classic chemical that everyone uses is dimethyl death. So you have a chemical in your workplace that you use called dimethyl death, and you know that's just made up. But there is no standard for it. And there is no literature available on its toxicity. But the lab, there's an environmental service lab that you use, and they can measure the concentration of dimethyl death. So if you take an air sample and send it to them, they can measure it and give you a number. Let's say you're curious what your exposure is, and so you do take a sample, send it to the lab, they measure it, and they give you a number for the concentration. How useful is your number?
Not that much different than two.
Exactly. Without a reference, it basically means nothing. It means nothing. So the lab will be glad to take your money, though, to analyze the sample, but it will do you no good because there is no standard. And there are plenty of things for which there are no standards. I think I mentioned this, but I've heard, I don't know how true this is still, but there are around 10,000 new chemicals created every year. We have standards for less than 1,000. So there are a lot of chemicals out there that we just don't know. That's part of the reason we're so reactive is it would take a lot of time and money to test all of those and develop standards based on their toxicity. We just don't have that time or money. And so we wait till people start dying, and then we test it out and figure out, what we should do about it. All right, so what's the answer for this? Sorry? 594? Is that?
408.3.
All right, so we have some differences.
Just what, 593.9.
Okay. So we have some who got that and some who got
For the 8 hour or
the 8 hour.
I got
408.3.
408.3.
Okay, so that probably makes sense because I can see how that's probably the basic, without looking at the next slide. But
That's the 8 hour.
so yeah, so the basic TWA is 594, but this number isn't super helpful, like I was mentioning, because we can't compare this to the Pell or any standard, because this is for 330 minutes. The standard is based off of 8 hours. So we have to assume, I'd never go through the process of assuming, okay, we have concentration 0 times 150 minutes. I never do that. I just skip straight to the full equation. A sort of abbreviated equation, a shorthand, I guess you could say. So this is the number that we're going to compare to the standard. That's the one that's actually useful. All right, so now I would really...
What if the time is in excess of 8 hours?
Good question. So we'll talk about this again, but the quick answer is if you have, I'm going to say the Pell, it could be something else. And the Pell is based off of 8 hours. What you have to do is you have to take the ratio of the Pell, the 8 hour Pell, to, let's say you have a 10-hour shift. You do that. So let's say the Pell was 100 parts per million. We'll go with a gas. But you work a 10-hour shift. For the person working that shift, the Pell is actually, well, go like this, sorry. You multiply it by that ratio. So it's actually 80. So the Pell for someone working a 10-hour shift is 80 rather than 100. So you can see it comes down. So it's more conservative. Although you can imagine you have more time to be exposed. So anyway, this is the ratio of 8 to whatever the time is multiplied by your Pell. Oh, actually, I do want to do this. So let's go with 6 groups, I guess. So you three here. Oh, or if you guys want to, does someone already have an established group? Raise your hands. Okay, so you guys, you 3. All right, so why don't you 3 regroup? We'll have 6, and so some will double up. So you 2, you 2, you 2, and you 2. Is that okay? All right. So I'd like this group to take OSHA, this group to take MSHA, in the back, ACGIH, you guys NIOSH, you guys EPA, and I'll have you guys do ACGIH as well. Since I think it's probably the hardest one.
Oh,
So what I would like you to do is just be ready to tell us what it is, like a 1 or 2 sentence summary. What is it? And what is the abbreviation for their standard? And what does it mean? So I've been throwing out Pell. You're going to see stuff like that or things that are different. What is the term for their standard or guideline?
Three standards. So let's say we're assigning MSHA, so 3 standards for MSHA with.
Well, you guys can just OSHA, MSHA, you can just do the main one. Just do one. The main standard.
That's not this.
ACGIH is that. That's ACGIH. So it's, well, and we'll talk about what it is in just a minute. But you have OSHA. Wait, what do you guys have? Did I give you OSHA? Yeah.
So you're saying different standard.
Yeah. Yeah. For yeah, actually, it's sometimes it's interesting. I'm guessing maybe you find the same thing in aviation, but sometimes the different agencies or administrations are at odds a little bit with each other. An example is at the mine, they have a crushing facility, so they have a primary. They break the rock from like car-sized rock to football-sized rock in the primary, and then in the secondary it goes from football size to more like little pebble size. But anyway, in the secondary crusher it gets really dusty, making big rocks into little rocks. It's dusty, and MSHA told the mine to install ventilation fans to exhaust the dust out of the building. And EPA said, you can't do that. You need to keep the dust in the building so you don't expose the community that's nearby. So, like sometimes they don't agree.
There's something wrong with your side.
For okay, well, so you could just look up MSHA. You have MSHA? Look up MSHA on Wikipedia even. So, did I talk about crystalline silk? I did. So, first look up what MSHA is, and you know what MSHA is the hardest for silica. So I'll tell you what it is. So just find what MSHA is, and then what is the standard called. No, so just go ahead and search for MSHA, and
Yeah.
well, first I want you to be able to tell us what MSHA is, and then tell us what the standard is.
This is what it says.
Mm-hmm.
and health administration.
Good.
Wikipedia.
Yeah, Wikipedia is fine. So now look up MSHA's health standards. MSHA health standards and see what it says.
Above the Pell.
For you guys, just what does it mean? I'll tell you the crystalline silica because it's actually the most confusing of them all. And it's not straightforward. Yeah, just what do they call it? So it's a type of exposure limit. What is the name? So another 30 seconds.
Why am I known as just being like the slowest thing on the face of the planet?
Because you have
Action.
No, I didn't.
Yeah.
Mine safety and
All right, so let's get to it. So OSHA, tell us about OSHA.
OSHA, they have a Pell and exposure, permissible exposure limit of 50 micrograms per cubic meter, but an action level of 25 cubic meters or micrograms per cubic meter.
And that is an update, so I had to change the slides because they actually, anytime OSHA wants to update a standard, it has to go through Congress basically. So you can imagine how often they update standards all the time, right? Almost never. They're all outdated. They're based on science. You know, the ones that have not been updated are based on science from like the 50s and 60s. So but we've figured out a few more things since then about some of these chemicals.
What does RCS mean?
Respirable crystalline silica. So it's this. It's just easier to write than the whole thing. So what does OSHA stand for?
occupation safety company.
Good. Good. So this is part of the Department of Labor. You don't really have to remember this, but it's helpful if, like in the real world, not for the class, but for the real world. Part of the Department of Labor. And actually, one of the one of the impetuses, I don't know, one of the reasons that OSHA was created was actually pressure from business. And you can tell that by looking at the differences between OSHA and MSHA in the way the laws are written and where liability is transferred when someone messes up. In OSHA, there's more opportunity for you, the worker, to be cited and be liable than the company. Now, there's still plenty of things the company can do where they're liable, but there are more opportunities for with OSHA for you as the worker to be cited. All right, what's MSHA?
Central Mine Safety and Health Administration.
Good.
So they're responsible to enforce Federal Mine Act.
1976.
Mm-hmm. I want to make sure. So in OSHA, it's called the Pell, permissible exposure limit. So this is also part of the Department of Labor, and its reason for becoming was mostly pushing and pressure from unions and labor. So if you look at the laws within MSHA, there's a lot more. I mean, the company is responsible for most everything, just the way it's written. What is the exposure limit called? Well, so that's the standard. That's the code of federal. Yeah, that's the code of federal regulation. So we'll talk about the Pell, the permissible exposure limit for RCS in a minute from MSHA, but they're the same. So it's the same word, permissible exposure limit. And there are lots and lots of similarities between these two and some differences, but generally they're very similar. Obviously, mining is a little bit different than just kind of general industry. And so there are some things that are unique to each one, but ACGIH.
So ACGIH is the American Conference of Governmental Industrial Hygienists. And we found two different values. It was either 25 micrograms per liter or 50.
Okay,
Just kinda don't-
it's a good thing they're not, well, I mean, they are a business actually, but you don't, yeah, it used to be part of the government, but it's not anymore. It's not governmental, even though that's in their name. And if you were trying to pick a trendy name for business, that would not be it. But
So it's what, 50 milligrams per cubic meter, 8-hour PEL,
mhm,
and then action level is 25.
good. So it's called a TLV, or a threshold limit value. ACGIH used to be part of the government. Now it's not. It's private. And it's, so you can imagine it private, it's more of guidelines. They produce guidelines. They can't enforce anything. It's not the law.
So since we did ACGR, so
Mhm.
I found that it says 0.1 milligrams per cubic meter is the TLV, the threshold limit value.
Okay, for silica?
I think it was this one. TDC. Establish a permissible exposure limit of 0.1 milligrams. So it doesn't tell me what the TLV weight. Like it doesn't tell me.
Well, I think it's referring to an OSHA proposal right there.
Right.
So that might be published a little bit older. I'm not sure, but I believe it is 50. I mean, if you your book should tell you as well. 50 micrograms. So
That's 0.05 milligrams.
yes. So ACGIH tends to be more conservative because it's based on more recent science. So evidence is how they determine what the TLV should be, which is what you would hope. Evidence-based decisions, right? You want to base, and it's so, I don't know. Sometimes I get frustrated when I look at processes or systems or just decision making, and it's not evidence-based. Whether we're talking about business or politics or whatever, I don't know. The way I think, well, let's look at the evidence and see what might work best. Anyway, some of you have heard this from me, I think, but we, as part of one of my classes, well, I was TAing a class that took a tour of a foundry. So they work with molten metal, pour into forms and molds and stuff. It's has its share of hazards. But anyway, we were talking about the general manager, and at the end, she mentioned that just a few months ago, they had actually looked at their books and done the numbers to figure out that they were profitable. So they had been working for months or years, and they weren't totally sure if they were making money. And I like could not understand that. It made no sense to me. As a business, I think you'd really want to know, are we making money? Like, what products make us the most money? Let's focus on those. Anyway, so based on evidence, Nyash.
So yeah. So and I actually the National Institute of Occupational Safety and Health. And well, as far as the
guidelines, they use a recommended exposure limit.
Okay.
And for crystalline silica, it's 0.05 milligrams per meters cubed as a fine weighted average for up to 10 hours a day, 10 hours per day.
It should be an 8-hour, but
They're putting the CDC on this, and so it's discussing no more than 40 hours per work, up to 10 hours per work day. So it's still an 8-hour shift over 5 days.
okay.
The limit is 10 hours.
That's interesting. Yeah, is that like on a website or?
Yeah, it's on the CDC.gov.
Okay. So well, yeah. Okay. Oh, interesting. So
Or recommended exposure.
NIOSH is part of the CDC, which is part of the Department of Human and Health Services. So it is part of the government. But as they mentioned, what does the R stand for in REL? Recommended. So
what I'm referencing based off from him is mine is the permissible exposure.
okay.
Mine
So
discusses the 50 micrograms. Reputable free silica per meter cubed, and no more than a 10-hour workday for 40 hours.
So NIOSH is probably referencing the OSHA Pell there, as well as their own REL. So NIOSH produces the REL, and they'll reference that. The first place I go to if I'm curious on I'm telling you this now after you've looked it up, but is the NIOSH Pocket Guide for Chemical Hazards. They have an online version. There should be a link in the syllabus. Online version. They also have hard copies. I have hard copies in the lab, but I look there and I also look at the TLV book. And
Because this is updated more often.
so the REL, the pocket, well, yeah, yes. They don't update, they update the web version of the Pocket Guide, but the hard copy, once it's done, it's done. So yeah, to be honest, the best resource is the TLV booklet if you want to be up to date and have the most protective guidelines. All right, and EPA, that was kind of a hard one. Okay.
Found this from the EPA website. It says National Primary and Secondary Ambient Air Quality Standard. And the listed value is 150 micrograms per cubic meter for 24-hour average, 50 micrograms per cubic meter.
Okay. I'm less familiar with the EPA standards, just particularly for silica. We'll see. I don't remember what theirs is, but they do care quite a bit about particulates and dust.
It has all the other ones that we just talked about, specifically saying silica.
Mm-hmm. Okay. The EPA, well, real quick about NIOSH, I forgot to mention this. So they do research. They are like the little red-headed stepchild compared to the NIH, if you've ever heard of that. Has anyone heard of NIH? Yeah. So, I mean, for good reason. NIOSH focuses on just occupational safety and health. NIH is like everything. So they get, billions of dollars in funding, and they're more in the millions. But anyway, so they get less money, but they do research on safety and health, and they produce their own recommended exposure limits. EPA is kind of like trying to think of a good analogy here, but of these agencies or administrations, is there one you think has more power than the others? Huh? Any other thoughts?
I think it depends on where, power where, on the job site?
Well,
OSHA.
so, and some of the power is in the books written down, but not exercised as much. And so some are more active. I would say the EPA is, although, so OSHA does have authority to shut down a job site. MSHA does have authority to shut down a mine. EPA has authority to shut down either. I think the agency or administration that has a reputation of doing that more is EPA. At least, I don't know for sure, but EPA, you know what? I'm forgetting which department they're in the government, but they are the environment surrounding their creation was very much. So we'll talk about this at the end of the course, but it was public outcry from kids being born with defects and stuff like that. And so when you have that environment and an agency or administration gets created, they tend to have more teeth than some of the others. So they have big teeth, and some of the others don't quite have the same amount of teeth. Anyway, so EPA tends to be very strict about their guidelines. Or they're not guidelines, they're standards. So real quick, I decided to take care of the MSHA Pell because for silica, it's kind of funny what they do. So you guys were right for OSHA, 0.05 milligrams. You guys talked about that's 50 micrograms. For MSHA, it's this little equation that OSHA used to use as well until they updated. Basically, the lab analyzes the sample to determine the percentage of silica. And there are different types of silica, but so you would get this percentage from the lab, and so every sample that you take has its own Pell. Every sample has a different Pell. So there is not one Pell that applies to every silica sample you take. Every single one is different based on the percent of silica in the sample. So you probably don't need to know that equation unless you get a job in mining. Don't worry about remembering that one. Just know that it's an equation and every sample has its own Pell. NIOSH and ACGIH agree on their guidelines. Maybe I'm lying. I have to see if that has been updated recently in the 2018 version for the TLV book. So we're not going to get too much into this, but silica has a few different polymorphs. Actually has a lot, but there are 3 that are commonly focused on: quartz, cristobalite, and tritiumite. And ACGIH has a TLV for each. Okay, parts per million. I like this way of visualizing parts per million. So if you had $1 million and I took $1, you think you'd miss that dollar very much? Probably not. That's just to give you a sense for what 1 part per million is. It's not very much. There are different ways we can determine the parts per million for any contaminant, but it does literally mean for every, say, regular air molecule in this room, if we're talking about carbon monoxide, how many carbon monoxide molecules are there for every million regular air molecules? And that's what the parts per million is, basically, for, say, carbon monoxide. So if we have 1 ppm of carbon monoxide, it means that there are 999,999 parts of regular air in this room. There shouldn't be very much CO. We could measure. I think I have instruments for, I do have an instrument for carbon monoxide, but let's change that to CO2. How much CO2 do you think is in this room? We're just Is it about the same or higher than CO? A lot higher. A lot higher. Why? Yeah, every time we breathe out, there's more CO2 in this room. That's why it's important to have a good HVAC system, good air movement in a room. We'll talk about indoor air quality later. Okay, that's right in the way. So we can determine the concentration in parts per million if we know the volume of the contaminant and the volume of the area. Or area is probably not a good, you could think of that as, well, the volume of air, just regular air. That's probably a better way to think of that. So let's say I had, let's go with something. I was thinking of paintball and the CO2 cartridges. But that's just not very much CO2. So what if we had a let's say a 20-liter bottle of CO2, and we released it into this room. And let's say that, so there's some unit conversion going to be involved here. Refer to any source online you'd like to find the conversions. I'll tell you which ones you're going to need. You'll have to look them up. But so you have 20 liters of CO2. I have a 20-liter CO2 canister, and I open it up. It'd be kind of mean, and let it disperse into this room. Close the door, turn off the HVAC system, and just see who gets a headache first. And let's say the room is, well, let's see, these are probably 2 feet by 4 feet. So 1, 2, 3, 4, 5.5. What is that? 22 feet by 1, 2, 3, 4. 18, 36. So it's 24 feet by 36 feet by 8-foot ceiling. What is the concentration in parts per million of CO2 in the room? Assume we're gonna talk about partial pressures in a minute, but assume that all of it escapes and it all mixes into the room evenly. Okay, so yes.
But P equals nRT, right? So the molecules of CO2.
We're not getting to Pivner yet.
No, I know, but the molecules of CO2 depend on both volume and pressure and temperature of said CO2. So 20 liters of high pressure CO2 is going to have more molecules than 20 liters of low pressure CO2. So the pressure of CO2 is important.
Right.
So ppm is going to depend on the pressure of that cylinder that you release to atmospheric conditions.
Assume equal pressures. I guess that's the detail I'm missing here. So assume equal pressures in the canister and the room. We are going to get to the ideal gas law. So you're thinking ahead, and that's good. But assume for now that the pressures are equal, and that it disperses evenly across the room, and there's no extra air coming in and out. So you have a volume here, but it's not the same volume here. You have a volume here in liters. You need to get these two volumes to be the same thing. So once you get them in the same units, then you can use this equation. Volume of the contaminant divided by the volume of the actual air, and then multiply by a million.
You're in square foot? Is that what this one is?
What happens if you multiply two measures of feet together? You get square feet. What if you multiply a third then?
Cube.
Cubic. So volume is going to be in a cube. Yes, cubic feet. we usually, we talk about meters, we talk about feet. So we're a cube. If it was area, we would just talk about one face. Two-dimensional. So there are two conversions. I mean, you can just like Google this, and they'll give you a conversion calculator to go straight from cubic feet to liters. If I didn't have that, I would use cubic feet. I would change cubic feet to cubic meters, and then cubic meters to liters. I know this conversion off the top of my head. I just don't know this one. Now I'd have to look that one up.
$195,726 liters. That seem right?
Curious, did you use an online converter that jumped straight to liters, or okay? I'm I don't care if you guys do that.
Foot equals 28.317
liters. I do recognize that. 28 point what?
28.317.
Okay. So let me just show you real quickly how I would do that if it was me. First, I'd find, let's find this number. What is the area in cubic feet here? Our volume?
1,912.
Cubic feet in this room, approximately. You saw that was a quick and dirty way to get the volume in here. So I would go like this. This is from I think it was from my Gen Chem days, my classes. It might have been physics. I don't know. But the equation says we need the volume of the contaminant on top. So I write 20 liters, of CO2. And the volume of the air, the rest of the air, on bottom. So that's 6,912 cubic feet. But I can't divide liters by feet. That's impossible. We need to convert it first. So I Google it, and I find out that for every every cubic foot, for every one, like this, cubic foot, I have 317.32 liters. So these cancel, these and these cancel. I don't want units, right? It's really a unitless number. I'm just wondering how many parts of CO2 per part air. And then I'm going to multiply by 10 to the 6. Does that make sense? Keeping track of your units. A fancy word to use for that is dimensional or unit analysis. It's important to just keep track of units. You can also check your answers by making sure that your units can. If all the units work out, there's a good chance you did it right. If you have crazy units that don't make sense, then something may be wrong.
What did you say, times what?
10 to the 6 times a million.
Oh.
All right. So we're not to Pivner yet, the ideal gas law, but we will in a few lectures. Let's see. A few. This is sort of a preview. Each constituent of air has a partial, what's called a partial pressure. It's the pressure that it exerts, and each gas in the air will have its own partial pressure. So in regular air, what kind of gases, especially say in this room with a bunch of us in here breathing, what gases, if we were to sample, would we find? Okay, which is the largest component of air, right? What else? Hopefully we'd find oxygen. If we don't, then we have a problem. So we'd find CO2, and there are a bunch of others, huh? There are a bunch of others. We would probably find a little bit of CO. Let's see. Electronics sometimes produce some other stuff that you don't want to breathe, but it's so little that, I'm thinking of gases. So like photocopiers will produce benzene, which is a carcinogen. You don't want to, if you start work and your office is right next to the photocopiers, you should ask, can I get my own office, or, work somewhere else, please. I mean, if it's like one and you don't do a lot of copying, it's not going to matter. But if there are like 6 copy machines in the room and they're always going, maybe you should ask. Like, it's really noisy in here. Can I work somewhere else? It's distracting. And no. Yeah. You don't want that anyway. So they're probably not going to be as productive in there either. But anyway, maybe some people like that. I don't know. But so nitrogen will have its own partial pressure, the pressure that it is exerting. Oxygen will have its own pressure it exerts on everything around. So let's focus on CO2, since we're focusing on CO2. So if we know the partial pressure of CO2, then, and we know the pressure of all the air combined together, then we can find its concentration in parts per million. At sea level, does anyone know what the total pressure is that's exerted? So maybe we should have just covered Pivner. I mean, we're covering some of it, but if you went up to the absolute ends of the atmosphere, I don't even know what that's called. It's not even stratosphere, it's higher than that. But troposphere? I figured someone in here would know. And so there's a column of air from, let's say, this cute one, a square meter spot on the Earth. There's a column of air above it. And although air doesn't weigh a lot, if you take the weight of that column of air, it actually exerts a pretty decent amount of pressure on us. If we didn't have that, I mean, it's not a pleasant thought, but what would happen to you if you were in space and not in a pressurized system?
Blood boils.
Okay. And once you'd probably kind of like, your body would expand, and I don't know what would happen, but anyway, hopefully no one has ever experienced that. So it wouldn't be pleasant though. You would be dead.
Yeah.
Okay. I figured someone would know.
3,000 feet is where your blood boils.
Okay, well, I figured someone in here would probably know, but anyway, you don't want that to happen. So that there is a pressure that just the weight of that air, it pushes on us, and that's called atmospheric pressure. At sea level, that's 1 ATM, or 1 atmosphere. That's nice and easy, but that's not always the units we use. 1 atmosphere is 760 millimeters of mercury. They're like, I don't know how many ways to measure pressure. Lots of ways to measure pressure. We're going to stick with a few. we're not going to focus tons on pressure, but in the class, it's just important to have a basic concept. And can someone look up what 1 ATM is, or what the pressure is at, what is the elevation here? 50, huh?
5,045.
Oh, that's the airport? Okay, close enough. Close enough. Or you could look at 5,000. So you should be able to find a calculator, something online that'll tell you. It's pretty, but look at, so the issue is at sea level, there's more air to push down. If you go up 5,000 feet, on a mountain or, where we are on a highland, there's less air. And so the pressure is going to be less. There's less air above you than if you were at sea level. That's why, your ears pop and stuff, because there's just less air, less pressure. So what is it in ATMs or in millimeters mercury? We can convert if we don't get it in millimeter mercury. Should be like in the 600s, I think. I know 10.
Because you're asking altitude in feet, it's giving you pressure in inches of mercury, not
Right.
millimeters.
Inches is
All right, we can convert.
24.
Yeah.
Oh, good point. 20.
Millimeters, 632 meters.
632. It should be in the 600s. That makes sense. We'll go with 630. 630 millimeters of mercury. Yeah, like you could use inches mercury. You could use inches water. You could use millimeters water. Lots of, yeah, you could use pascals. You could use PSI. There's too many. We'll focus on just a few. Okay, so the total pressure, if we were to go stand outside of the column of air on us, would be 630, well, in the room too, but millimeters of mercury. It's just easier to visualize outside. So that is our PA. Now, I'm not sure how we'd measure this, but if we knew that the partial pressure due to the CO2 in the room was, let's say 80 millimeters of mercury. So this is the partial pressure of CO2. What would our parts per million, our concentration of CO2 be? So we use this equation here.
.1269.
Okay,
I mean, it's
that's the proportion of CO2, and then once you multiply it by a million, so 190,000, whatever that is.
126,000.
Oh, okay. All right, so we'd set it up this way.
Is the PA in that equation
Partial pressure of just the air.
air?
You can think of it as total. A was probably not the best subscript, choice. All right. Now, man, this is just right at the wrong place, but I guess that makes sense. So, again, we're not talking about Pivnert today or the ideal gas law, but if you're assuming normal temperature and pressure, so if you're not at sea level and it's not room temperature, you can't assume this, but we usually, for the sake of the problems, we assume it anyway, because if you don't, then it turns into a much bigger, more complex equation. Anyway, so we assume NTP, normal temperature and pressure. If you assume that, you can use this equation to convert from ppm to milligrams cubic to milligrams per cubic meter. And MW is the molecular weight. Man, we really should have just talked about Pivnert. That's okay. Because I want to talk about molecular weight, but we'll just not worry about it. Just know that it's a thing, and we'll talk about it more. Right now, we're just kind of basic math stuff. Now, if this is if we have the milligrams per cubic meter, but how would we change this around so that we could calculate this if we had parts per million? Good, so we'd multiply both sides by that and divide by 24.45. So we would end up with milligrams per cubic meter equals molecular weight times the parts per million divided by 24.45. Just some quick cross multiplying.
What did you get for the EPPM?
That's ppm. I just wrote it ppm here.
80 divided by 630.
Oh, up here? It was 127. What was it?
26,984.
Okay, so using that example, again, assuming this is the partial pressure of carbon dioxide in the room, let's calculate the concentration. So we could determine the mass of the CO2 in the room if we had that information, but 126.9, let's round it to just 127 even. So, and the molecular weight of carbon dioxide. We'll get the exact. .01. So when we assume NTP, you don't have to worry about the units for molecular weight. It does have units, but 44, basically 44. And here you're going to plug in 127,000. So that's the concentration. I'm just using what we did before as an example. And we got about 127,000. So we take the concentration in ppm, multiply it by the molecular weight, and divide by 24.45, and that will give us this number. What is it? Should be a big number.
How did you get the 44, sir?
Get what?
The 44 for the molecular.
This is, I looked it up. So that is that number will never change for CO2.
So it's 228,500.
Okay. Just a little bit. Good. So now that conversion in itself isn't super helpful because generally the standards for CO2 are expressed in parts per million. That's another, you got to compare the apples to the apples. And this is really high. So a partial pressure of 80 millimeters of mercury for CO2 is unrealistic. Yeah, I mean, that's a lot of CO2. We would have more than headaches if that's what it was at. All right. Dang it. So we will look at TWAs for mixtures, and then, yeah, our last bit of math. We'll take a short break after the math. I'll give you like a 15-minute intro to calibration, and then we'll go over there. Okay, it's often that you aren't just dealing with one chemical, one contaminant. You might have multiple. An example would be in aircraft manufacturing, when you are applying primer and paint, there's a lot of stuff in here. It's not just one thing, not just acetone. There's going to be hexavalent chromium. There's probably going to be toluene, xylene, other nasty stuff that you don't really want to be breathing. So when we have a mixture, we can determine the safety of the mixture by using this equation here. So when things have similar toxicological effects or similar health effects, then you can look at the additive exposure effects. So it's only when they have similar health effects. If they have completely different health effects, you have to treat them separate. If they have similar health effects, you add them together. So it's harder to be in compliance if you have a mixture of, let's say, a bunch of solvents that do the same thing to people. It's going to be harder to maintain compliance than if you have a mixture of solvents that do completely different things to people. So you take the concentration. Basically what you're doing is you're taking a ratio of the concentration to the PEL, and this is C. Think of that as the TWA. The TWA to the PEL for contaminant 1, the TWA to the PEL for contaminant 2, etc. If you add those ratios together and it's less than 1, then you're good. You're in compliance anyway. You don't want to be close to 1. So let's look at our example here. Xylene, toluene, and acetone, which are all solvents. They could all be found in paints and primers. So hex chrome would do something different. That's why it wouldn't be on this list. But someone look up, oh, never mind. So we have 55 parts per million. We'll just do this together. For xylene, we have, for toluene, 30 parts per million. And for acetone, we have 450. You can also get a sense for chemicals toxicity by looking at the exposure limits. So of these three, which do you think is generally more toxic? Xylene, because it has a PEL of 100 versus 200. It's when you see stuff that's in the, I mean, if we're using parts per, if it's like 1 or in the parts per billion, then you know you want to stay away from that stuff. Don't mess around with it.
Say that again?
It's just a like a quick and dirty way of gauging the toxicity of different chemicals. So if I look at these three chemicals and I see these PELs,
Yeah.
I'm going to be most
With the lows.
concerned about that one. Oh, I mean, now maybe we use a ton of acetone in our process and not very much xylene, stuff that has xylene, and so maybe I'm not that concerned about it. But all things being equal, if I had the same amount, a gallon of each, I'm more concerned about xylene than acetone. And then we plug in the PELs. So here we have 100 parts per million, 200, and 1,000. So we take those ratios, and what do we get? So this is going to be what, 0.55. This is 0.15, and this is 0.45. 1.15, is that right? So we're over 1. That means we're not good. We need to work on bringing that down. At the very least, have respirators, but we'll talk about respiratory protection later, and it's not as simple as just handing out respirators. All right, let's take a 5-minute break, and then we'll talk about calibration, and that'll give us an hour to go over some hands-on.
What does CPPM stand for? What's the C?
The concentration in parts per million.
So in theory, if you know exactly what the partial pressures are, those two numbers should be the same, right? In theory, if you know exactly what the volume and the partial pressures.
I don't know, but you could be right. I have to think about that.
It's both for concentrations and part per million. It looks like
Oh.
it's just two different ways of tackling.
I see what you're
One
saying.
via pressure, one via volume. But based on the ideal gas law, assuming that you know precisely what those two things are, it should work out.
It should, yeah, it should.
Assuming all things being pressures are equal.
Mhm.
Temperatures are equal.
It should, yeah. I guess, yeah, if you maintained all the other variables the same, then they should.
But that's where it gets tricky, right? Because if you change pressure at all, it throws all that stuff off.
Yeah, I mean, the stuff we do in here is assume, there's like a list of assumptions that we're making when we do these equations. But
But you're using pumps to move air.
yeah, so
Just changing the pressure.
So what we're doing with concentrations is mostly the purpose of the equations we're looking at now is either getting a quick estimate of concentrations in a room, say if it's indoor air quality, we want to get a quick estimate without actually measuring it, or if we have units, if we've been given the concentration in one set of units and we need to convert it to another, which sometimes happens. So the lab might report milligrams per cubic meter for something, but the PEL or the TLV is in parts per million. So we have to change that. But if that really did happen, then we have to throw out all those assumptions, because chances are we didn't take the sample at normal temperature and pressure, guaranteed. I mean,
It's really hard to do here because we're out.
well, yeah, here you would never be able to. It'd have to be like San Diego, at sea level.
So can we do a real world problem?
We will. We're building. So some of these you do use, for sometimes sampling and actually measuring is expensive, or you don't have the equipment for it. And if you want to estimate what a concentration would be let's say in a room with indoor air quality, then that's probably the way I would do it. But you have to have a big fat asterisk there. This is a guess.
Does the school have any labs that are certified?
We don't have anything like that. Not that I know of.
My understanding, that means you have to be at standard atmosphere and temperature and maintain a certain level of filtration for years.
Yeah.
I think in Maryland, we had a lab. Regardless of weather, it was guaranteed to be at 1 atmosphere.
Wow.
68, whatever the atmosphere.
I don't think we have that. Daytona might have something like that. I think they may have a barometric chamber.
They do.
Okay.
Yeah.
So they may be able to manipulate things. So, yeah. So really, part of what we're doing today is also unit conversions, and you do have to do that. just in general, maybe not the exact scenarios we covered, but knowing how to convert units from one thing to another is helpful in real life, in industrial hygiene. Or
Can we use some sort of a,
I think we're done with the math, so
I don't know, do we do in-class testing or is it online?
it's going to be online.
Okay, so we can use the internet to find out the
Conversions, yeah. I'm not, I like to try to simulate a certification exam, but I think I explained the issues with the lockout browser, whatever it's called, and I didn't like it, so we're not going to worry about that. If you guys want to use an online conversion calculator, that's okay. I mean, in the real world, that's what you're going to use. Yeah. So, it's kind of a balance there between real world and what you'd find on a certification exam, but kind of in between. Okay. So this is a big flow chart that I made to be helpful, and I think maybe it's just more confusing than helpful. Everything up here that says lab typically is done by the lab. You're not going to do it. You will determine the sampling media type you need depending on what you're sampling for. So let's say it is aircraft. You work for Boeing or Airbus or somebody who manufactures aircraft, and you've got this crew applying paint to a new aircraft and primer, and I don't know what else, but I mean, a nice witch's brew of stuff. And you want to do some sampling. So let's say it's for hexavalent chromium, because that's a nasty one. And it is, you do find it in aircraft manufacturing. You're going to have to look up. So we'll talk about these processes more later. Right now we're focused on calibration, but you're going to have to figure out what type of sampling do you have to do. If this is hexavalent chromium, what kind of pump what kind of equipment do I need? There's sampling media involved, so the actual thing that collects the hex chrome and you send to the lab. What kind of flow rate do I need on my pump? So these methods for sampling are standardized, and they give you some wiggle room, but you have to be within the ranges. So you got to figure out what flow rate can I use, and you're going to have to determine a target volume and what sampling time you would need. So the method generally will tell you have to use a flow rate between these ranges, and you need a volume between these ranges, or sometimes it says this number. Like you need to try and get a volume of air that equals this number. So we talked about how the number we get is a surrogate for reality. It's as close as we can get to what the person was actually exposed to, but it's not really. It's somewhere close to that, hopefully. This entire process its purpose is to approximate that exposure number as closely as possible, because the method is designed around a certain target volume of air. So the pump has to pull a certain amount of air. We have to calibrate our pump to know what the flow rate is, and we have to keep track of our sampling time to then be able to estimate the sample volume. Let's look at that equation real quick. I'm not sure it's on these slides, but the volume equals the flow multiplied by the sampling time. And we need that volume because the method says it's got to be in this range or it's not really valid. So they've tested it at this volume, and they tested it at other volumes, and they found that, well, this volume works the best, or this range of volumes works the best. And they'll tell us the flow rate we need. So this flow rate is what our pump's flow rate is. And now I haven't used the newer pumps, but there are pumps that will estimate flow rate through the whole day as it samples. We don't have pumps like that. Like I said, I've never used them. That would be nice to have, though. Those pumps automatically adjust for pressure and temperature. They're pretty fancy. Old school doesn't do that. We calibrate the pump before we sample. So this column is for the actual taking the sample. Then we calibrate the pump after. And calibrate really is more like confirming the flow. Beforehand, we might adjust the pump settings to get to the flow rate we want. Afterwards, we're just seeing what the number is. We're not going to adjust anything. So we take the average of those two flow rates. So we have our pre and our post divided by 2. So that's all it is. And then we keep track of how long we sampled, usually in minutes. You know, it's nice if you can get 480 minutes. That's what you want. You don't want to sample for 100 minutes and then make a somewhat large assumption that the rest of the day's exposures were like that, 100 minutes. You want to try and get the full day if you can. So the purpose of what we're doing is just making sure that the pump is at about the right flow rate, you know, within 5%. And then after we're done sampling, we calibrate again, measure the flow rate to get an average. And then with our sampling time, we can estimate the volume. And remember, the concentration is the mass per volume. So we're going to use this later. We provide this to the lab, actually. So the lab will measure mass of our sample, and they'll take the volume we gave them from our calculation to come up with a concentration, and this is the number they give us. We're trying to lay out the whole process here, and that is what we use to calculate a TWA that we compare to the PEL. So it's a little bit of a process, right?
So they gave us the concept.
Yes. So we
Just have to provide the.
We figure out the flow rate we should use and what volume we're trying to reach. You know, it's our target. So we're going to try and get that volume. We calibrate the flow. So we think it'll give, you know, and we decide how long are we going to sample? Well, 480 minutes. So we can figure that out. We calibrate the pump. We take our sample. We calibrate again and get the average flow. And then with our sample time and flow, we figure out the volume. We send our thing to the lab, and that's why we pay them money, you know, sometimes lots of money for them to use their fancy equipment and measure the mass. So the lab will estimate, we send it to the lab will estimate the concentration, they give us the number, and then we calculate the time weighted average. Yeah. Good question. You want to use a filter that's similar to what you are going to use, but you don't want to use the actual filter because it'll be contaminated. Now, if you're sampling for something crazy, I mean, let's say you are calibrating in your nice, clean office, there's probably not a lot of hexavalent chromium in there, okay? And so you're probably not going to contaminate your filter, the sample, but you could. So you usually, we'll talk about that over there, but you'll have some media that you just write on there calibration, and you use that to calibrate until you start to see that it's degrading or something. But you'll calibrate with that, but you'll have your real samples over here, and you don't open them or touch them or whatever until you're ready to go take your sample. Does that make sense? Contamination. Now, if conditions are very different, or if you're, say you're, I think my computer's going to die, but that's okay. If you're sampling, let's say you're going to go take samples in Colorado at an altitude, at an elevation of like 10,000 feet. You don't want to calibrate, you know, in Denver and then drive up to where you go. I mean, I'm thinking of mine sites, but there could be other stuff. You want to drive up there because the pressure is different, the temperature is different, and that's going to affect your.
My main question more is to, I'm calibrating my office. My office is one controlled environment compared to the lab controlled environment? Why not just calibrate within that same controlled environment?
You could. It would just depend on the risk of contamination. If there's not really a risk of contaminating in the, like,
What do you like contamination?
so,
Source media, right?
right,
Or
you are, but usually as when you're done calibrating, then you'll put your real samples on and go set them up. And so you don't want to necessarily be opening the media, the sample media. I'm thinking of the aircraft manufacturing facility in this big hangar with guys spraying primer and stuff all over. You know, there is hex chrome in there, so you don't want to necessarily open up your sample in there because there could be some hex chrome that gets on it. But that wasn't part of their exposure. That was just you putting the sample on. Does that make sense?
I get it.
Yeah, and I agree. Once we've walked through some of this, I think when you come back to this, it might make a little bit more sense. But I want to show the end, like what the end goal is, so you understand why we have to go through all these steps in the first place. But you know, that question would depend. So like if I'm sampling for dust, I don't want to go to the dusty area necessarily because I might contaminate my samples. If it's if there's not a huge change in temperature, pressure, conditions, it's fine to calibrate in your office and then go to wherever you're going to go. But if there is a huge difference, like your office is a nice, 75 or whatever, and the facility is 125 degrees, like in Phoenix or something, maybe you do then want to calibrate out in the field. A soap bubble flow meter is a primary standard for calibrating. We're not going to do this, but this is think of the old school method. You get this little container full of water, you put soap in it, you set it at the bottom of this flask, you hook your pump up to it, and then with a stopwatch, again, old school. I had to do this, but I can't do this. You turn on your pump, you hit the timer, and you watch this bubble go up the thing. And it's a known volume, so this might be 1 liter. And so as soon as your bubble hits the 1 liter line, you stop the stopwatch. And you use the time and the volume. So you use this equation, rearrange to find out your flow rate, which, so would that be Q equals V over T. Liters per minute or whatever. You would get it into that form. But we're not, you'll never do that ever, I don't think, except in a lab. But that's the gold standard. Don't know why, because, there could be so much error in just like hitting the stopwatch. But anyway, we're not going to watch that. This is more of what you would do. We don't have this exact calibrator, but there's a frictionless piston flow meter or calibrator. It has a little piston in here inside a chamber with a known volume. You hook your pump up and your sampling media. We'll talk about how to hook that up. Then when you turn on the pump, you tell the calibrator to go, basically, and it knows the volume, it measures the time, and it will give you the flow rate. So this is considered a pseudo primary standard, but it's pretty much what everyone uses for a sampling pump. We'll talk about other types of calibration. So this is the type of pump we have, and that is the type of calibrator we have. Well, it's the mirror image, you might notice, and then we have our sample media. So we will have the tube that we're going to use in the field. This tube is simply for calibration purposes, although if we have a really long tube, what does that do to our pump's ability to pull the air? It adds resistance. So you don't want a really long tube between here because that's not representative of reality. One of the goals in your calibration, so it's a good point, Steve, is you want your calibration conditions to be representative of the conditions where you're going to take the sample. Otherwise, you're going to have a disparity there. So you want to use, so if you're calibrating this pump for this type of media, you want to use this pump with this type of media in the field. And if it's, I mean, ideally the same pump with the same tubing, just you use your sample media instead of the calibrator one for contamination purposes. So that is one thing to keep in mind. Calibration conditions are representative of the actual sampling conditions. This is a typical filter cassette. We'll go in and take some apart. But it's got multiple pieces. We won't take it all the way apart, but there's a backside with ring, and that's my computer dying.